In this video, we're going to explore one of the counterintuitive aspects of critical point analysis that shows up with single variable versus multivariable comparisons. If we looked at single variable calculus and we had a single local minimum with no other critical points, so it doesn't go up and hit another critical point. We're not doing that. We just have one critical point and that's it. One location where the tangent plane or the tangent line in a single variable is horizontal. With that single critical point in mind, then as long as the function is continuous, it can never go back down again, right? We can never turn around and go back down, because if we were to do that, we would have to introduce another critical point, but we're not allowed to. So maybe the function flattens out, but never quite flattens out completely, or maybe it goes larger and larger. But no matter what we do, this point here is a local minimum. And then we can conclude that that single local minimum is guaranteed to also be the global minimum. Now, it takes some stronger theory than this to actually prove that, but we can try our best to sketch some way that this is not the case, and we're going to fail. There's always going to be either another critical point introduced, or the function isn't continuous, or something else. In single variable calculus, if there's one local min, the function has to go up outside of that in either direction, and that means we're at a global min overall. We're going to see an interesting fact that that's not necessarily the case when we look at double variables, two variable functions. It sometimes happens, but it's not guaranteed in the same strong way as it is here. Let's consider, for example, this function here, x squared times this y cubic plus a y squared. We start by identifying the critical points of the function, and then we'll follow up by classifying them. The x derivative, there's only one x, it's the x squared, we take its derivative. And then the y squared with x, this derivative is 0. We take the y derivative, the x squared is a multiplier, and then differentiating the y term here with the cubic, we're going to get 3, 1 minus y all squared, and just a little bit careful, we also get a negative 1 for the chain rule inside of that, and then plus 2y. Then, to identify critical points, we set both of those equal to 0. What that gives us here is 2x. We can actually get rid of the 2. Because it equals 0, we can divide through by 2. This other expression here is a little more complicated, but we can at least bring some of the constants out front. We have negative 3x squared, 1 minus y all squared, plus 2y. Equation 1 and equation 2. Now, equation 1 only has two ways to be solved. It's in factored form already, so either x equals 0 or y equals 1. We can then take each of those and explore whether they solve the second equation. Let's start with the x equals 0. We'll put that into equation 2 and see what we get. That'll give us 0 for this term, times 1 minus y all squared, plus 2y equals 0. Well, that 0 multiplier wipes out that entire first term, and we get y equals 0. So 0, 0 is a critical point. We're combining our y value of 0 with the x equals 0 that led to it. And the other possibility is y equals 1. We sub that into 2 and see how those could work together. And this is interesting because we're going to get negative 3x squareds times 0 plus 1, or plus 2 times 1. And that is interesting because we have a 0 multiplier here. Got to be careful. 0 times this is 0. And so we get 2 equals 0. That's a big no-no. That's not really giving us anything useful. So we don't get any additional critical points out of this y equals 1 possibility. We explored it, it led to a dead end, and it left us with a single critical point. All right, let's investigate what type of critical point that is. We're given a little heads up here that we're looking for a local minimum. we've copied over the first derivative information to begin with. Then we find the second derivatives. We're going to have 2, 1 minus y all cubed. The y second derivative, got to be a little bit careful here. In fact, let's tidy this up the same way we did earlier. It's easier to differentiate this expression when it's been tidied up. We take the y derivative of this. The only y's are here. The negative 3x squareds come along for the ride. We're going to have 2, 1 minus y's to the 1, and then the derivative inside gives us another negative plus 2. And that bears tidying up as well. That will be positive. 3 times 2 is 6. 6x squared, 1 minus y, plus 2. Then last but not least, our xy derivative. It'll be easier to work with this term. Taking the y derivative of it, we'll have 2x, 3, 1 minus y all squared, again times a negative 1 for the chain rule inside. And that is also negative 6, x, 1 minus y all squared. All right, so we have all of our values. And then what we can do is substitute in our 0, 0 critical point. If we do that, we're going to get 2 times 1, which is positive 2. The y second derivative is going to equal 0. That all gets wiped out. Plus 2. And last but not least, our mixed partial derivative at the point 0, 0 is going to be 0 because of that multiplier of x. What that gives us is a discriminant of xx, yy, 2 times 2, minus 0 squared, that's 4. Key thing is that's positive, so the concavities match or are the same. And we also had, say, fxx is positive, which is concave up. And all of that together through the second derivative test means that we have something concave up around our point. So the point 0, 0 is a local minimum. All right, so what we found so far is that there is a single critical point and it is a local minimum. And at this point, if we were in single variable world, if we had a graph just of x against y and we'd found a single minimum, we would be able to also conclude that this is also a global minimum. We're going to see it's not quite that straightforward in this case here. If we take a look at our function, we see this interesting term, 1 minus y all cubed. And so if we let, say, x equal 1, then f with y's left over in it is just 1 minus y cubed plus y squared. And we can play our usual game looking for what this function does in the long run in certain directions. If we let y go towards positive infinity, then 1 minus y is going to go towards negative infinity because we're doing 1 minus that value. Well, that means the 1 minus y cubed is going to go towards negative infinity as well. And the other term, the plus y squared, is going to be smaller. We've seen this several times in the course. As the values get large, the highest power is the term that's going to dominate. So in other words, our function can approach negative infinity. Our function can drop, 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 and that means there can be no global minimum. So even though we've only found one critical point, and it was a local minimum, somehow with multivariate functions, when we're talking in 3D here, somehow there's a way to escape that minimum and get down lower without creating a peak somewhere else. Let's take a look at that graphically, looking at the surface of this particular function here and see how that plays out. Here's the surface of that function and the matching contour diagram. To reinforce where we were at the point 0, 0. So the minimum that we found on the contour diagram was here. However, as we just explored, as y gets larger and larger, this function can go down towards infinity. So we can clearly see f approaching negative infinity, so there's no global minimum. But how do we get there without actually or accidentally inducing another maximum? Well, you can imagine starting at this point here on the contour diagram, and we just sort of go over the shoulder. There's no single highest point along the route here, but I can go over, going this way, I can get to higher and higher values. If we go in positive y in this diagram, we're going to get to higher and higher values for a little bit. We go to 0.5, then we go to 1, then we go to 2, but then we can end up going downhill after that. So what we've captured is a path that we can follow on the map, which translates to a path like this on the surface, where we go over a shoulder of a mountain, but it's not a most extreme point because there's still a direction I can go up from there. And there's no other critical points at all. There's no other locations where we see this nested loops of contours that indicate a local max or local mins. So this is the kind of interesting shape that we can get, not using horribly complicated functions, but moderately complicated formulas, where we can get interesting and new behaviors that we did not see in single variable calculus.